And we're going to start back this afternoon, our time, working with functions. So earlier today, we were working with a couple of operations that I believe I sort of justified with the statement of "it works, just trust me." So we've been using, say, the print function. In our last module, we were working with len, to calculate the length of sequences. So we've talked about and also worked with built-in functions. And somewhere there's a specification for what actually happens when those functions are called. Somewhere there's a script or a library that defines len and print and range. And what we're going to do now is work through the basics of how to write our own functions. So take little packets of something like procedures, something that you would do often, at various points, various branches of some code that you may be writing. You want to formalize and sort of package this set of procedures into a way that is then callable, just like how we've been calling range and print and len, and that's a function. So we're going to learn how to define functions. So functions are extremely useful for not only being able to compartmentalize and formalize typical sets of calculations or procedures in your software. It's also a really good way to be able to actually clean up your code. I mean, it doesn't take long for CompuSol models even to start reaching hundreds of lines of code if you're doing a lot of advanced modeling in Python. And so writing functions and later today writing your own data types, those are excellent ways to be able to formalize what you're doing in your your advanced models and your complicated scripts, make everything very easily debuggable, testable, and shareable. And so we're going to work through those details now. In the very least, a function definition has a couple of basic components. The first being a header. And the header, which is this first line here, first tells Python that you're declaring the definition of a function. And you do this, I'm going to go ahead and move over and get some code going as well. You do this notifying Python that you're describing a function by first using the keyword def. You notice in my IDE that def turns orange, much like none or and def. And in the header, the next thing that we specify is the name of our function. In this example here, this is writing a function called isEven. I'm going to write one called isOdd. Def is odd. That is the name of my function. Def is odd. And then the next component of our header is a specification of all the arguments that can be passed to our function. When we reviewed working with the range function, we found that we could pass one argument to iterate from 0 to some past number, iterating over every integer. When we passed 2 arguments, we could specify both the beginning and the end of the range over which we were iterating. And when we passed 3 arguments, the third argument we could use to specify by what step we do our iterations. The function definitions in these headers specifies the arguments that can be passed In our case, we're going to keep it simple and just say we have a set of arguments that can be passed to our function and not worry so much about optional features and arguments. And we're just going to say that if our function can take an argument, the argument being passed to our function from the outside world, we start some parentheses, and we just give a name to the argument that can be passed according to however we want to name it. And we're going to use that name to refer to what's passed when we work with the argument inside of our function. For example, if we want to calculate or develop a function that returns whether or not a passed value is odd, we could call the argument passed to our function I, and in all of the procedures that we perform inside of our function, we'll refer to whatever is passed to our function as I. And in a very simple case, in general, we want to return a bool that states whether or not something passed to our function is odd. And we can test this by saying the remainder of I divided by 2, is it or is it not equal to 0? If it's not, then I is odd. This is our test. If the remainder of I divided by 2 is not equal to 0, we'll call that result. So that's the result of our test for whether or not this variable I, whatever it is, test whether or not it is odd. Now you'll notice that the body, which is all of the code that actually defines what goes on inside the function, all of this is indented. And the function definition will continue no matter what we write until Python finds a line in the code with no indent. So there's nothing in particular that has to specify whether or not the body of a function has terminated, except it finds as technically 2 lines with no return or with no indentation. Now, a function like what we've been using would return something. We've been, say, doing for in range of something, or assigning the returned value of len to some variable that then we would print or something like that. The functions actually don't necessarily have to return anything. In fact, lots of Python functions that are employed in complicated software actually return nothing at all, but instead cause changes to the variables that are passed to the function itself, or even modify something that's defined outside of the function. So it's necessary in Python to specify explicitly what is returned by this function when it is called. Something specifies what's returned by len in the definition of len. And we do this with the keyword shown here in the example, and I'm going to type it here as well. The keyword is return. And then whatever precedes or whatever follows return is what is returned by our function when it's called. And in this case, if we want to return result, then we will say return result. Question in the chat, Is there a rule to the information that is written within, and then in what's called the doc string? Yeah, so there's another component here that is technically not mandatory, though strongly encouraged. And that's the space in between the header and the body. And that is what's called the doc string, or the documentation string. And the doc string is a special kind of string. It's called a multi-line string. We've not worked with these today. We certainly will in CompuCell. And a multi-line string is a string that can have multiple lines. I'm just going to make a little space below my working function. A multi-line string in general is a string that is specified within a set of 3 quotations. Now, S can be worked with just like any other string, except that with a multi-line string, it's implied by all of the returns. I can do this for as many lines as I want. And it's understood that within the actual data of this string, there are line returns. And according to wherever I return in my string. Now a doc string is like that. Yes, excellent point, Tareen. Antimony code is written using multi-line strings in CompuCell. So there will be a few days where you get lots of practice with working with multi-line strings. Now in this case for doc strings, like shown here, doc strings are formatted as multi-line strings, and you'll notice when I start one of these in my IDE, PyCharm will automatically generate fields for me to fill out. But this data, this string, is not available inside the body of my function. Rather, what will happen is that IDEs like PyCharm or lots of peripheral Python tools can read those strings and actually automatically generate documentation about your code that's generated from the doc strings that you wrote. For example, I write this is a function, and then come down here and say f equals is odd. Oftentimes you get things like when I pull up the documentation on this function, you'll notice it says this is a function, and it knows this from my doc string. So the doc strings are not mandatory, but highly encouraged and incredibly useful, both for yourself and for others. This is a not a mandatory thing, but definitely an excellent way to keep track of what you're doing. It's a great way to communicate to others what the purpose of a function is. Oftentimes I write these just to keep track of what I'm trying to do as I'm developing functions and things like that. So for now, we'll just keep a little reference here. This is a function. And so now in this case, the function that I've prototyped here, this is complete. We've got a header that tells Python writing a function, specifies a name for my function, which is odd. I specify that my function can take one argument, which I'm referring to as I. And in my function will test whether or not the argument passed to it is odd, and then will return the result of that test. So question, what is the benefit of docstring over using the pound symbol for a comment? That's debatable. There are, for example, parsers that can generate documentation about code that's been written from comments. And in a lot of ways, there are ways to communicate with tools that you're using by actually specifying keyword commands in the comments. The standard for writing Python functions and classes is to include a multi-line docstring in Python 3. This has sort of been a refined process and sort of like structure over time, but there are a couple of different formats that you can follow. As you see here, this example here is a little bit older. I use a parser that works on this a little bit differently, so the comments that I write might look a little bit different from the comments that someone else writes. But the standard is to use the multi-line strings for documenting functions and classes. Excuse me. Okay, so now we have a workable function. And we can use this just like we've been using len or range or dir or anything else. So we can just test this and say print is odd 0. You notice when my command is too close to my function body, I get a warning here in my IDE, expected 2 blank lines after class or function definition. 2 blank lines meaning that there's no indentation in these 2 lines that follow my function definition. So this is how Python will understand not only the branches and say the logic and control flow, it will also understand developing infrastructure like this, like functions, or later for defining classes for custom data types. So when I print is odd of 0, I get false. For 1, I get true. 2, I get false. That's the basics of how to write just a very simple function. Now, there is a lot of complexity that begins from this point to do with functions. You can, for example, write a function within a function. For example, just like we were able to write, say, branches within branches when writing for loops and if statements and so on and so forth, we can also do things like write functions within functions. We can say within our function is odd, we can define another function that says, say we'll call it test. And test takes the argument called x, and we'll just return our actual test. The remainder of x divided by 2, does it not equal 0? In which case, we can just return test of I. And that is perfectly valid. You can also refer to functions and treat them like data, like they are objects. So I can say my function equals is odd. And then use this function that we've defined, but with this completely different, well, differently named reference. Say if we print my function of 3, and I still get true. Now, probably most complicated, at least easiest to complicate, is differences in what's called scope. I'm going to reverse all of this fancy business for now, since we have not much need for it at the moment. And instead, I'm going to point out this observation here. In our function, we've had this, let's say, at least in my case, I named the argument that can be passed into my function. I named it I. And I do my test on whatever's passed into my function by referring to it with the name I. Now, out here, after my function definition, when I go to actually use it, can I say I equals is odd of, say, 2? Is there any problem with that? They have the same name, but are they referring to the same thing? And the answer is they're not the same thing. In this case, I is defined within the body of this function. And the reason for that is because it's declared here as an argument in the function, and then is only defined within the body of the function. This is called the scope. I, in this case, as it's defined here in this argument, is only defined within the scope of the body of the function, and then afterward is no longer defined. It's not a real thing outside of the body of my function, whereas out here, outside of my function definition, I has absolutely nothing to do with the I that's named as my argument for my function. It's just referring to the return value of my function. So here may be named the same, but not referring to the same thing. And the difference in scope is what makes this possible. Now, here is something fun that has lots to do with this issue of variable scope. So this function that we've defined here, this is dividing by 2, testing the remainder and seeing if it is not equal to 0, and that's our test for whether or not our function is odd. Now, let's try another function. Let's call it, you want to follow along with me, let's call it, say def and is divisible by. And we're going to have one argument for this function as well. Let's also call it, let's call it x. So our function is going to be named is divisible by, and it's going to have also one argument. We're going to name it x. Give it a doc string if you like. This is another function. And now what we're going to do is we're going to declare another result that we're going to return. But follow along carefully with what's done here. I'm going to declare a variable outside of my function, and before it, I'm going to call it b. I'm going to say b is equal to 2.0. So b is a float. It's equal to 2.0. And it's going to be declared before my new function is divisible by. Now, we'll go back into our function. Our new function is divisible by, and what we're going to return is the test of whether or not the passed argument x into our function, is it divisible by b. B being defined before the function Yet you'll notice that in the case of my IDE, I have something popping up highlighting this B when I click on it within the function and recognizing it from where it was declared before the function. And what that means, what is occurring here, is that variables defined in the what's called the outer scope, outside of the function, before it, that information is inherited into the scope of the function body. So anything that has been declared before my function, I can refer to varying degrees of whether or not you can actually change values or so on and so forth. You can refer to, say, previously defined functions, previously defined data, you can refer to that from within inside the actual body of new functions. So now I can say C equals is divisible by, say, 3.0. And now I can change how this function behaves, is divisible by. I can change how that function behaves by changing some of the data that was defined before the function definition. So for example, here, testing whether or not 3 is divisible by 2, 2 being defined up here for B, 3 being passed into the new function as an argument, and then the function actually doing the calculation to see if the past argument is divisible by the previously defined data. When I run this, I get that it's false. Now you'll notice that when I change my past argument to 4, 4 is divisible by B equals 2, so that's fine. If I change my argument back to 3, then change B also to equal 3, I get true again. Outer scope, then the data from that outer scope gets inherited into this inner scope. This is also true for functions that are defined within functions. So here, if I have a function defined within my function, for example, not only can B be referred to within my inner function, but so can X, because the function body of is divisible by is the outer scope for the function body of test. And so this information will propagate from here to here to here. Now, a lot of why we bring this up is because this causes, well, we know of instances where this has caused some major headaches when it comes to how to propagate information in model specification when we actually go to do some of the implementations for CompuCell Python. And so what we want to have right now is a working knowledge of how this information will pass from one scope to another, so that when we go to actually do our model specification, we don't find that things are getting strange as far as where variables are being modified, within functions and later in class definitions as well. Now, one thing to note here, as discussed a little bit earlier, functions don't necessarily have to return anything. Hence why we must, if we want our function to actually return something, we have to explicitly state what the returned thing is. And then the question arises, well, what happens if we don't specify anything? What if say I do, and my new function is divisible by, if I do that calculation, but don't return anything, well then what is C? C here being a result of calling is divisible by 3.0. It was testing whether or not the value is divisible by whatever the value of B is. But now the function isn't returning anything. So what happens when I call this function and actually try to assign a value to it? And I find that when I assign that value to C and then print C, I get none. So this is one of the many examples of why none is so special and sort of ubiquitous across not just Python, but programming languages in general. Sort of the idea of referring to something like nothing. And in this case, when returning nothing from a function, something is returned. The thing that is returned is none. And of course, this can be used in things like control flow and things like that. So one can say, we go back and fix our function and say this is actually returning something now. Well, this is a Boolean that's being returned, which means that these functions can then be used as conditionals and so on and so forth. Or in the case of if returning nothing, you can say if the return value of my function is none, so on and so forth. All right, so I'd like to let me check my time real quick. Okay, so I'd actually like to give everyone 5 minutes or so and work out this exercise. The exercise is write a function that calculates the nth Fibonacci number. The definition of which is shown here for your convenience. So this is a piecewise definition. For n equals 0, the value is 0. For n equals 1, the value is 1. And for all n greater than 1, there's a recursive definition here. So I'll give everyone 5 minutes. Maybe try at that a little bit, see how it goes, and then we'll reconvene. All right. Let's see how everyone is doing. We took a poll a couple, yeah, there we go. All right, so I think we still have some people working. We'll give it another, yeah, there's another poll going. Give everyone a couple more minutes. All right. Let's go through this together. I'm gonna go ahead and just clear my script here to start fresh. I'm gonna start by just naming a function. It's customary to give things simple names. Helps understand complicated ideas. Let's just name a new function, say def, and call it fib. And the equations on the slide refer to the nth number. So let's say we're going to take one argument n and start our body by concluding the header with a colon. I'm going to make a tiny doc string, just n fib number, and start the actual calculations. So you have three cases here. Actually, we have four cases, but we'll deal with the ones that are expressed here mathematically. That is that we have some branching to do according to the input that we get that's passed to our function. Namely, that if n is equal to 0, then the number we would like to return, according to the definition, if n equals 0, then the Fibonacci number for n equals 0 is 0. In a Python function, you can declare, excuse me, return at multiple points in the function body, just under the pretense that writing something after a return function within the same level of indentation isn't going to do anything, because at this level, in this branch, after return has been called, nothing else executes. The program will return whatever is returned and continue on outside of the function. But otherwise, it's perfectly valid to say that in a branch, you can just simply return a value. And also, in another branch, say when n equals 1, which we implement as elif, and then the condition n equals 1. In this case, the definition says when n equals 1, the Fibonacci number is 1. And lastly, at least as far as implementing our definition, good practice, we'll just say else, meaning for all other cases. And now we're going to return something. And the question is, what is it that we actually return? In the case of the Fibonacci number definition, we actually calculate other Fibonacci numbers. In this case, we can do something like this. Our function is defining the nth Fibonacci number, so we can just say return a call to our function with different values passed as arguments. This function, fib, calls itself. And so long as nothing in the actual flow of logic with doing these calculations results in an infinite recursion, meaning that the function just repeatedly calls itself over and over and over, then this is perfectly valid. Now, what's not valid here is, say, what happens when I pass a negative number to fib? Or what happens when I pass a float? Because one thing to note about Python is that by default, no constraints are placed on anything that's passed around as to what type of data it has to be. This is, I won't say both a strength and weakness, but this is a perk and also a burden of working with Python, is that nothing per se necessitates what has to be passed into this function, except that something has to be passed in. And for any enforcement of the characteristics of the data that can be passed, we must enforce explicitly. For example, we can prevent our function from trying to execute and instead notify the user through an error or a warning. We can prevent executing when the passed argument is negative by first checking and saying if n is less than 0, and then we're going to generate an error. We've seen errors earlier today. We saw things like type errors. We saw things like value error. It's very straightforward to be able to create and then throw an error yourself in your own code. And you can do this with the keyword raise. There are lots of predefined types of exceptions that can be thrown. These are all just mostly implying information about the type of error that's been raised, or exception that's been raised. All of them come from the same type of exception, just called exception. So in this case, we can be a little bit informative, and let's say that if someone passes a negative value into our function, we can raise a value error. And a value is a type. Value error is a type, excuse me. And when we pass to it a string, say cannot be negative. And what we'll find is that if we pass a negative number to our function, it won't try to calculate. say fib -1, we get a value error. Cannot be negative. Can be even more rigorous in our checks, which is not a bad idea for having a recursive definition like this, by also using a built-in function to do type checking. And the function is called isInstance. isInstance takes 2 arguments and returns a bool, and it tests whether or not something that's been passed to it is of a data type that's also passed. And what I mean by that is we can say if not isInstance, meaning the negation of the result of isInstance, and say pass the argument that's been passed into our function in and the type to test against, which is int. Say if in is not an instance of the int type, and we can raise another error. Raise type error. Not an int. And so now try to calculate the nth Fibonacci number of the string in, then get a type error, not an int. This is how all of this is implemented, and everything that you work with in Python when coming across these errors, you find these all the time. Usually be what's called a traceback provided that will give you information about where the error was or the exception was thrown, like in here, and how that all propagated through the information with calls across lots of scripts and functions and so on and so forth. It all boils down to just increasing complexity of these same types of structures.
If I may make a small parenthesis, the error you got actually was before your raise.
It was. Yeah, this is an excellent point, Giuliano. Thank you. So now you'll notice here, Giuliano's pointed out that I did get a type error, and I didn't notice because I wrote in a type error to be raised that the type error I got was actually not the type error that I myself raised, but rather at line 5. The issue here being that a string type was passed into the function fib, and then the first thing that was calculated was a test for whether or not a string is less than the int 0. And then, as Giuliano pointed out, there is no comparison defined between a string, which is what was passed, and an int, which is what was being tested against. And so what's necessary to do here is to reverse the order. First, we must test whether or not an int was passed into the function in the first place, and if it was not, then we throw an error and nothing else occurs in our function. Having validated the type, then we can test to make sure that it's in proper domain for the Fibonacci numbers by raising a value error if it's not, in which case the function stops evaluating. Now, having passed all of our checks, type fib of, say, 5 and print it. $12, $16, should get numbers that you can well validate against Wikipedia or your favorite discrete mathematics textbook. So I'll leave this up for a little bit longer. I can also make this available, but this would be something like a final solution that exercises quite a lot of what we've crashed through today so far. All right. Now, very quickly, we're going to get a little more, we're going to learn this more through practice, both later today and throughout the week than we'll really spend much time on today. But I think I've seen a question to this effect in the chat as well, which is modules, how to get stuff into our script to be able to use when writing software. For example, we have built-in functions like range, len, dir, and then types that are known like strings, ints, floats, so on and so forth. What about other stuff? Say something that I wrote that you would like to use in your script, or say something that's distributed in your Python environment like Tellurium. Import Tellurium as TE. Many of you have been looking at that line at the top of your Jupyter notebook since this morning. And this is done through modules. So we've defined, for example, a function in this script. The name of my script is just called scratch.py. Now, if I'm in another script, it's possible for me to write something like what many of you have with your Tellurium import statement. It's possible to write something like from scratch, my script, import fib, which is to say that the definitions that are defined in this script or in some script or set of scripts defined by someone else, to take information like functions, data values, data types, and import them into what I'm currently developing. And we saw this in our first example today when importing Tellurium with te.load a and so on and so forth. Much of even the Python library, you can try this out now, much of the Python library, well, the Python library is distributed along, is distributed along with a Python, in a Python environment, which means that if you have Python available to you like you do right now, then you can test out importing from modules right now. And there are a lot of them. So for example, say you'd like to calculate the square root of something. You have one way of being able to do that, which is say x equals, and we can say 2 and to the power of 0.5. If you recall from earlier this morning, the power operator being 2 asterisks. Square root is taking something to the power of 0.5. Another way of doing this is in a library that's distributed with the Python, it's called interpreter, and that library is called the math library. And you can do something like this. From math, import sqrt, which is the square root function, which somewhere has defined some def square root and an argument. That function is defined in the math module, in which case I can also say y equals square root of 2. Scripts like what we've written today with defining new functions, as well as with the exercises that we'll do in our next module for defining classes, and later this week, this coming week, for the actual model specification that we do with all of the different modules. It's possible to take the definitions of those functions, those types, those calculations, so on and so forth, and import them from some other Python script where they're defined into the Python script that you're working on. And then you can define new definitions that build off of those definitions, or work with those predefined types. You can specify then functions here in new scripts that then can be used in other scripts. So you can sort of break up, the operations and the procedures and the definitions according to, whatever project you may be working on, but break it up into more manageable chunks of simpler tasks, simpler definitions, simpler data types, and be able to sort of construct things in this, sort of virtual reality of definitions and objects and types and so on and so forth. And much of that is done by treating Python scripts as modules and importing definitions from one script into another using this sort of functionality. Now, this can get fairly nuanced and at times quite subtle. For example, and we'll get a little more practice with this in the next module, you'll often find that when working with modules, you can find things like from math, maybe math isn't a good example. From SciPy dot. And now there are things into this package called SciPy with sub packages, stats, FFT for fast Fourier transform, cluster. If I do stats and then dot, and now I have more things. So this is directory structures. The directory SciPy, subdirectory stats, and then within stats, there are all of these scripts that have actual definitions that can then be imported into this script. So navigation for importing and so on and so forth in Python is done using these dots. For all the built-in libraries like math, there are no dots necessary. Python always knows where they are, so you don't have to worry about any of that. All right, well, now we may go over with the rest of this because as was mentioned earlier today, dictionaries, arguably the most heavily used of the types in CompuCell-based modeling. Dictionaries are a very particular type and a very useful one for many reasons in general, as well as in the type of work that we're going to do this week and that we'll often do when doing CompuCell-based modeling and Python-based modeling in general. And dictionaries are special because dictionaries are in some senses like lists or tuples or strings, some kind of sequence, in that with the sequences, there's a one-dimensional structure where we always have the capability to be able to specify an index. And with an index or with a slice, be able to access elements in our sequence. The index 0 being the first element, the index -1 being the last element. Dictionaries are special, again, for a lot of reasons, but one of the reasons they're extremely useful is because with a Python dictionary, you specify what could be thought of as the index for a value in a dictionary. So instead of doing something like passing an integer to a bracket on a dictionary, say I have some dictionaries, just going to call it my dictionary. Dictionaries can be instantiated using curly brackets. So square brackets were lists, parentheses were tuples, dictionaries are curly brackets. And now, whereas in the lists or the tuples or also the strings, we could just start specifying data in a sequence and an order would be followed according to the order of the inputs. Dictionaries can instead specify what's called a key. And a key will act like an index on a list, except that the key is also data. For example, I can specify a dictionary and specify pairs of keys by which I can index something, and then a corresponding value that corresponds to that key. And I do this using first a declaration of the key. Say I want to have a key of 5. And I would like to have a corresponding value of the string A, and I can specify this using a colon. 5 here is the key, A key, excuse me, and then A is the value of the dictionary that corresponds to the key 5. The key is unique for the dictionary. The value is not, in that I can specify a key also equal to the string A. And with that key goes a corresponding value of, say, 6. Here now, the key 5 in my dictionary corresponds to a value of the string A, and the key that is the string A corresponds to a value of 6. And this can be used as follows. So now that this declaration has been made, I can say my dictionary, and when I use a square bracket like a list, but instead pass the string A, anyone have a guess as to what I'll get? About 6. The value in a dictionary that corresponds to a particular key. Here in the picture in this slide, Anna is a key that corresponds to a value of B. Denise is a key that corresponds to a value of A. John, a key, A plus is a value. Katie is a key, A is another value. And the values can then be referenced by their corresponding keys. Notice that this is heterogeneous data. We've got an int being used here as a key, and then a string as a value, and then a string as a key, and an int as a value. This is pretty non-restrictive. Can get very complicated when it comes to custom data types, but for everything that we'll be interested in for this week, all of it can be used for keys or values in dictionaries. So if we test this out and say print the value of the dictionary that corresponds to the key A, we already know we'll get 6 as defined here. And likewise, we should find that the value that corresponds to a key of 5 in my dictionary, as defined here, should return A. Question in the chat: is there any way to make a dictionary by transposing 2 lists? So if I had something like, I don't think I understand. Yeah, thank you, Jim. Yeah, so with having, say, something like 2 lists, you have A equals 1, 2, and 3, and B equals 2, 3, and 4, then it's possible to do things like for AI and A, and for BI and B, my dictionary of AI equals BI.
I don't think that would do quite what you wanted. Oh, would it?
Yeah, so what this
Because
is,
you want to pair, you want to walk it step by step through. So you want the ith index of the.
yeah, so what you'll notice here is that values, you can have, say, multiple values all corresponding to the same value throughout a dictionary, whereas the keys in a dictionary are unique in that when doing these sorts of iterations, one cannot specify multiple values to a single key in a dictionary. So if I do something like reverse this ordering, where I'm iterating over B for every element in A, and I'm assigning AI to BI, I'm accessing BI multiple times and assigning different values to it, and that's overriding the same to the same key, placing different values that correspond to that same key. So you can see an example of that here. And yeah, Giuliano, yeah, brings up zip. Zip has nice functionality to be able to do paired iterations like this. This is the sort of thing you can do 1,000 different ways. Now, there are some, as you might expect, dare I say, hope for, lots of operations defined on dictionaries. So there's, of course, the built-in operation of actually doing lookup, which is to say getting a value that corresponds to a particular key with the corresponding exception key error, which is thrown when trying to access a key that is not defined for a dictionary. So my dictionary has defined values for the keys that are the int 5 and the string A. And you'll notice here in line 3, I tried to access the value corresponding to the int A or int 4, and that's not defined. And so I get a key error. And it tells me what the key was that I tried to look up, and the program terminates. Now, with that in mind, keys and values can be assigned to dictionaries dynamically, in that this line that I just attempted, which is to say, get the value in my dictionary that corresponds to a key of 4. This throws an error because that's not been defined. Whereas what I can say is that I would like to declare a new key in my dictionary with the corresponding value. In this case, I'm going to say that along with my initial definition, I'm also going to then add a new value that is a string that says new value. And that's going to correspond to a key of the integer 4. So you can add keys and values dynamically like this. You can do things like tests and iterations. So there are a couple of different ways to do iterations over the data that's defined in dictionaries. One can, for example, get all of the keys in a dictionary by using the function defined on the dictionary called keys. And one can iterate over these, for example, in a for loop as follows. One can say for k in my dictionary dot keys, and then just print k and see what's going on in k right now. K has the keys 5, A, and 4. You can also do things like, say, generate a list of the keys by saying my keys equals, and let's pass to the actual list type, my dictionary.keys. And when we print my keys, now we have a list that corresponds to all of the keys in the dictionary. You can also ask things like, for example, let's print the result of the test. Let's see if 6 is in my dictionary. We see we get a Boolean. Test for whether or not 6 is in my dictionary. Now let's see if, say, 5 is in my dictionary. It sure is. And now let's see if A, the string A, you see that it's false. Now the thing is, A is in my dictionary, but it's a value, not a key. And so you'll see here that a test like this, when asking, is something in a dictionary, what one is really asking is something a key in the dictionary? Not a value, or not a key or value, but is it a key? Now, just like in lists, you can delete elements in a couple of different ways. There's, of course, the del element that we sort of blasted by when discussing lists. And so to delete a particular element, we can reference it by key. Say, for example, added here dynamically the string new value with much enthusiasm, and assign that to a key of 4, and then we can just go through and delete that with the del. Added it, moved it, Just like the keys argument, you can also get the values in a dictionary, much like the keys argument. Set function is values. A6 new value. And just like the keys, it can also construct a list, so on and so forth. This can also be iterated over. So now expanding on this a little bit with these built-in, what are called iterables. Let's do one more, and that is a very useful function to find on dictionaries. The function is called items. And items actually iterates returning a tuple. And that tuple is every key and value in a dictionary. Meaning every key value pair defined in a dictionary. So here, when we say for K, comma V, this is a tuple. In my dictionary.items, what this is saying is for every pair of key and value. And so when I say print this, I get every key, 5 and A, B and 6, 4 and new value. Another particularity that's important to note about dictionaries is that the data in a dictionary, while each key and value are paired, the ordering of key value pairs for the standard dictionary is not particular. It does not make any difference how you order the inputs of data when adding them dynamically. The actual ordering in memory for dictionaries is not guaranteed, whereas in lists it is. When you build a list with a particular order, the order of that list, unless modified by you or someone else, is respected, and that is not the case with dictionaries. Again, there can be duplicate values in a dictionary, but the keys must be unique because they are something like indices. And we won't get too much into I don't want to get into the weeds on this detail, but the requirement for whether or not something can be stored inside a dictionary, the criterion is that it must be what's called hashable. And I don't want to dive into the details on that right now, but in general, if you find that you can't load something into a dictionary and it's causing some sort of error, it has everything to do with whether or not the object you're trying to put in a dictionary is hashable. Okay, we've done most of this. Like the lists and tuples and strings, there are lots of other definitions defined. For example, we'll just close out with this, and I'll leave up this exercise for those of you who would like to work through the break. For example, if we would like to, say, remove a key and value from a dictionary, the dictionary has a method called pop. And much like the list, we will pass the key that we would like to have removed or popped from the dictionary. So if I say pass my dictionary and pop, I'm going to pass the key that I would like to remove. from my dictionary. And when I print it, there you go. It's got 5 and A, and then 4 and new value, but no B and 6.